cloudburst is one of nature's most sudden and dramatic weather phenomena, and it has long been a subject of curiosity and concern because of the intensity with which it strikes and the destruction it can cause. Unlike normal rainfall, which can be predicted with a certain degree of accuracy and usually spreads across a wider region, a cloudburst is highly localized and extremely intense. It occurs when an unusually large amount of rain falls over a very small area in a very short span of time, often just a few minutes to an hour. To understand what makes a cloudburst unique, we need to break down its key features, its performance aspects in terms of intensity and impact, the natural design elements that give rise to it, and the unique points that make it different from ordinary rain showers or storms. The key feature of a cloudburst is the sheer intensity of rainfall. While in normal heavy rain, the rate might be a few millimeters per hour. In a cloudburst, the rainfall rate can exceed 100 millimeters or more in just 1 hour, sometimes even higher. To put this in perspective, this amount of rain could equal what an area might otherwise receive in several days or even weeks. This condensed and sudden downpour overwhelms the soil, rivers, and drainage systems, leading almost immediately to flash floods and landslides. Another key feature is its localization. A cloudburst typically affects an area of less than 20 to 30 square kilometers. This means that one village or town may experience torrential flooding, while a neighboring village just a few kilometers away may remain relatively dry. This localized nature makes cloudbursts very difficult to predict with precision, adding to their mystery and danger. The performance aspect of a cloudburst lies in the speed and intensity with which it impacts the environment and human settlements. When rain of such magnitude pours down suddenly, the ground cannot absorb it quickly enough, especially in mountainous or hilly regions where most cloudbursts are observed. This results in instant runoff, turning small streams into raging rivers within minutes. The performance of the phenomenon in terms of destructive capacity is unmatched compared to regular rainfall. Roads are washed away, houses are damaged, and people can be trapped or swept away before they even have time to react. In technical meteorological terms, the performance is measured by the rainfall rate per unit area and the duration. But in layman's language, the performance of a cloudburst can be understood by how fast it transforms a calm area into a disaster zone. The design elements of a cloudburst are rooted in atmospheric science. The Earth's surface heats up, causing warm air currents to rise rapidly. These currents carry moisture upwards into the atmosphere, where they cool and condense to form clouds. In hilly or mountainous areas, these upward air movements are even stronger because of the natural barrier created by high terrain. When clouds get trapped along mountain slopes, they are unable to move freely, and the moisture accumulates within them. At some point, the cloud becomes overloaded and unstable. Instead of releasing its moisture gradually, as in normal rain, the cloud discharges it all at once in a concentrated burst. This design element explains why cloudbursts are so common in areas like the Himalayas in India, Pakistan, and Nepal, as well as in other mountain ranges around the world. Another aspect of the design is the role of convection currents and thunderclouds. Cumulonimbus clouds, which are tall, dense clouds often associated with thunderstorms, are the typical breeding ground for cloudbursts. They can extend several kilometers into the sky, carrying massive amounts of water vapor. When the balance of forces inside these clouds collapses, the result is a sudden downpour characteristic of a cloudburst. When we consider the unique selling points of a cloudburst as a phenomenon, several aspects stand out. First is its unpredictability. While weather departments can forecast heavy rain, predicting the exact location and timing of a cloudburst is still a challenge due to its highly localized nature. This unpredictability makes it a subject of fascination for scientists and fear for communities living in vulnerable areas. Second is its sheer power and speed, which set it apart from other forms of rainfall. The transformation it brings about in a short period of time is unmatched. A sunny or calm day can suddenly turn catastrophic within minutes. Third is its link with geography. Cloudbursts are most often associated with mountainous regions, which adds to their uniqueness. They are not just about meteorology, but also about the interaction between landforms and weather systems. This makes them different from other intense rain events that occur in flat plains or coastal areas. Another unique aspect of cloudbursts is their impact on human settlements and ecosystems. Unlike a gradual flood that builds up over days and gives people time to prepare, a cloudburst provides no warning. Villages nestled in valleys, near rivers, or on steep slopes are particularly at risk. The water rushes down slopes, sweeping away everything in its path. Bridges collapse, farmlands are destroyed, and roads are rendered unusable. For communities, this means sudden displacement, loss of property, and in many cases, loss of lives. From an ecological point of view, cloudbursts also alter landscapes. They can trigger landslides that reshape mountain slopes and deposit debris in rivers, altering their course. These changes can have long-term effects on local geography and water systems. If we examine the performance aspects in more detail, another factor to consider is the role of temperature and climate change. Rising global temperatures increase the capacity of air to hold moisture. This means that as the atmosphere warms, clouds can carry more water vapor than before. When these clouds collapse, the rainfall is correspondingly heavier. Scientists are increasingly studying whether climate change is making cloudbursts more frequent or more intense. The early evidence suggests that warming temperatures and changes in monsoon patterns are contributing to the conditions that favor cloudbursts. This adds another layer of complexity to the performance of this phenomenon, making it not just a natural event, but one intertwined with human-induced climate changes. Design elements also extend to the way cloudbursts are detected and studied. Meteorologists rely on radar systems, satellite imaging, and weather models to track the formation of cumulonimbus clouds and assess the risk of extreme rainfall. However, because cloudbursts occur over such a small area, even advanced technology struggles to pinpoint them in advance. This design limitation of weather forecasting highlights why cloudbursts remain among the least predictable, most dangerous weather events. Efforts are ongoing to improve detection through high-resolution models and localized weather stations. But the sudden nature of cloudbursts still poses a challenge. From a layman's perspective, the uniqueness of cloudbursts can be explained with simple comparisons. Imagine pouring a full bucket of water all at once over a small patch of ground instead of sprinkling it slowly over a wide area. The ground cannot absorb it quickly enough, so the water rushes away, creating mini streams and floods. That's essentially what a cloudburst does in nature, but on a much larger and more destructive scale. This image helps ordinary people grasp why cloudbursts are so devastating. Even though they may last for just a short time, another unique selling point is the way cloudbursts tie into cultural and local memory. In regions prone to them, such as the Himalayan foothills, stories of devastating cloudbursts are passed down through generations. Communities develop local wisdom and practices to respond to sudden floods, building homes on higher ground or avoiding construction near riverbeds. This cultural dimension makes cloudbursts not just a meteorological event, but also a lived reality that shapes societies and their resilient strategies. In addition, cloudbursts highlight the delicate balance between humans and the environment. As urbanization spreads into mountainous regions, deforestation and construction on slopes increase the risk of damage. Natural drainage channels are blocked, making floods worse when a cloudburst occurs. This means the human footprint plays a role in how destructive a cloudburst becomes. The same rainfall event in a forested, sparsely populated valley might cause less harm compared to one in a densely built-up mountain town. This human-environment interaction is another design element that determines the performance and consequences of cloudbursts. Overall, cloudbursts can be understood as nature's way of unleashing accumulated moisture in the most concentrated form. They stand out for their intensity, unpredictability, and localized impact. Their key features include sudden rainfall over a small area, rates exceeding 100 millimeters per hour, and a tendency to occur in mountainous regions. Their performance is marked by immediate flooding, landslides, and destruction, often overwhelming communities with no time to prepare. Their design elements involve strong upward air currents, trapped clouds in mountain ranges, and the collapse of cumulonimbus systems. Their unique selling points include unpredictability, sheer power, close connection with geography, cultural memory in affected regions, and the potential link to climate change. Understanding cloudbursts in these terms allows both experts and ordinary people to appreciate why they are different from normal rain and why they continue to be both a scientific challenge and a natural hazard.